A transformer produces scores everywhere. In attention, every token gets a score. At the output, every possible next token gets another score. But raw scores are not probabilities, and they do not tell the model how strongly each option should matter. And that's the job of Softmax. It takes a group of competing scores and turns them into weights that share a fixed budget. But Softmax is also one of the most misunderstood functions in deep learning. So as we see how it works, we are going to clear up 3 misconceptions about what it actually does. Suppose the model is completing the sentence, basically the famous sentence. The cat sat on the. It produces one raw score called the logit for every token in its vocabulary. For example, Matt might receive a score of 8.2, floor is 7.4, moon is 1.1, and banana negative 2.3. So we might think that the token with the highest logit has already been selected, right? It's actually not true. It has only received the highest score. These scores are not probabilities. They are the model's raw preferences. Softmax converts them into positive values that add up to 1. In this example, Matt receives about 69%, floor about 31%, moon about 0.06%, and banana almost 0. Now we have a probability distribution. So how does Softmax work? Softmax applies an exponential to every score, then divides each result by the total. But why we should use exponential? Why not divide logits directly? The problem with the direct division is that it can fail when values are negative or their sum is 0. Exponentiation maps every finite scores to a positive value while preserving the ranking. It also makes scores differences matter. For example, e to the power of 2 is about 7.39, while e to the power of 1 is about 2.72. That means that the logit that is 1 unit larger receives roughly 2.7 times as much on normalized weight. This is ML Guy, and we try to go under the hood of complex system to understand how they work. If you like such content, don't forget to subscribe our channel and like the video to help the recommendation system. Let's go back to the topic. So the another misconception is that Softmax evaluates each score independently. Actually, it doesn't. Every probability depends on every competing score. A logit only matters relative to other logits. All options share the fixed probability budget. Raise one probability and the others must give something up. Okay, now let's move inside self-attention. Suppose the model processes this sentence. The animal was tired, so it stopped. When processing the token it, a casual language model can attend only to it, an earlier position. Future tokens are masked. The model calculates query key similarity scores for the available tokens. To keep the example small, imagine that we consider only 4 eligible positions. Animal receives a score of 3.1. Was has the score of 0.8. So has the score of 0.5, and tired has a score of 1.4. Softmax converts those scores into attention weights. Animal might receive about 74%, was about 7%, so about 5%, and tired about 14%. So in a simpler terms, the weights control how much information from each position flows into the current representation. Attention also has a scaling problem. Its scores come from dot products between query and key vectors. As the key dimension grows, those dot products can become larger. Large differences can make Softmax extremely sharp, giving one position almost all the weight and making many gradients tiny. That is why scaled dot product attention divides the query key scores by the square root of the key dimension, and it does that before applying the Softmax. This keeps the scores in a more manageable range. Now return to the next token prediction. Does the model always choose the highest probability token? The answer for this question is also no. If we are talking about the greedy decoding, it selects the largest score. Sampling chooses according to the distribution. We have several parameters to play with. For example, temperature changes that distribution before sampling. A temperature below 1 makes the distribution sharper and more predictable. A temperature above 1 is flatter and creates more variety. Temperature is applied as softmax of the logits divided by t. For any positive temperature, this preserves their ranking. The largest logit remains the largest, but the probabilities around it change. So temperature matters mainly for sampling, not greedy decoding. And here is another misleading concept. A token with 70% probability is 70% likely to be factually correct. This is not true. It means that the token receives 70% of model's probability mass among the available choices. A model can assign high probability to something false. Softmax measures relative preference but not truth. You need to pay attention to it. Softmax also has trade-offs. For finite scores, it normally gives every option some non-zero weight, creating a dense distribution. It is sensitive to scale. Large differences make it sharp, while similar scores make it flat. And over a vocabulary containing tens of thousands of tokens, calculating the full distribution can be expensive. During greedy decoding, however, the full softmax is not always necessary. The largest logit will also produce the largest softmax probability. There's also a numerical issue. Exponentials can become extremely large. Real implementation therefore subtract the largest logit from every score before calculating softmax. Subtracting the same value from every logit preserves their relative differences. Exponentiating every shifted score introduces the same factor into the numerator and denominator, so that factor cancels. The final probabilities remain unchanged, but the calculation becomes safer. ReLU, GeLU, and SWIGLU transform values individually, but Softmax compares a group. It doesn't choose the winner. It creates the competition from which a winner can be chosen. Until the next video, good morning, good afternoon, and good evening. Bye.